Welcome everyone, this is Helmut Pitters, and we are going to talk about the number of cycles in a random permutation and about the number of segregating sites and how these two quantities jointly converge to the Brownian sheet. So we're looking at random Kingmans permutations, and the number of cycles of such a permutation we denote by Kn. We're going to look at Kingmans Coalescent and with mutations, and the number of segregating sites we're going to denote by Sn. And our main results will be a coupling of all of these models for all parameters, and we are going to look at the large N asymptotics of the joint distribution of Kn and Sn. So first of all, we're going to construct a Kingmans permutations on the numbers 1 up to n with parameter t1. So sigma 1 is the permutation with just one cycle containing the label 1. And once we have constructed sigma k, we find sigma k plus 1 as follows. So we place the label k plus 1 into a new cycle with probability t1 over t1 plus k minus 1. And otherwise, we pick an integer between 1 and k uniformly at random, and we place k plus 1 to the right of this integer. Then if zeta k is set to 1 if k starts a new cycle, the sequence zeta 2, zeta 3, and so forth is a sequence of independent Bernoulli trials. And if we sum them from 2 to n and add 1, we get exactly the number of cycles in sigma n. Now for an entirely different model, which is Kingmans Coalescent, it's a stochastic process with index by time t. It's a Markov process on the partitions of the natural numbers. It starts in the partition of singletons, and any two of its blocks merge at unit rate. Then pi of epsilon has a finite number of blocks almost surely for any epsilon greater than 0. And we're going to identify this coalescent pi with a tree on the leaves 1, 2, 3, and so forth in an obvious manner. Now here is a simulation of a subtree of the coalescent tree on 100 leaves. Now there are two interesting couplings sitting in this coalescent tree. So let Tk define the first time that pi reaches a partition of exactly k blocks. And then if we look at the process pi starting from Tn, so pi of Tn plus T, where T ranges over the positive reals, and we denote this process by pi n dagger, then this process is a coalescent starting with n blocks. And it has a tree corresponding to this coalescent, which we denote by Tn dagger. And this is nothing but the minimal subtree in the coalescent tree on n leaves that contains the root. On the other hand, we might also restrict the coalescent pi to n. And this process we call pi n star. And again, the pi n star induces the subtree in the coalescent tree spanned by the leaves 1 up to n. And we denote this tree by Tn star. And it's easy to see that pi n dagger and pi n star really are equal in distribution. However, the sequence pi n dagger, where n ranges over the natural numbers, does not have the same distribution as the sequence pi n star, where n ranges over the natural numbers. So we have two different couplings of objects that individually are equal in distribution. Now on top of the coalescent, we're going to run a Poisson-point process, which is independent of the coalescent, and it puts down points on the branches of the coalescent tree, each of which we interpret as a mutation. And these mutations induce another interesting partition of the natural numbers, defined as follows. So I and j are placed into the same block of this partition if and only if there is no mutation on the shortest path in the coalescent tree that connects I and j. And this partition is called the Allelic partition. We can restrict it to the first n natural numbers, which we denote by this restriction, we denote by an. So now for the coupling, we take a Poisson-point process on r plus squared with intensity lambda times 1/2 lambda, where lambda is the Lebesgue measure. And this process is independent of pi. Then by Ln, we're going to denote the total branch length of the coalescent tree restricted to n. And Mk is going to count the number of mutations, the number of points of this Poisson-point process on the rectangle built by the interval Lk minus 1 up to Lk times 0 T1, where T1 denotes the mutation rate. If we sum up all these mutations up to n to the 2t, then we just get the total number of mutations in a coalescent tree on n to the 2t leaves with mutation rate T1. Now notice that the Mk dagger, so the mutations in the temporal coupling, they are independent as k varies, whereas the Mk star are not. Moreover, if Mk of T1 is greater or equal to 1, we set Bk of T1 to equal 1 and 0 otherwise. So Bk is a Bernoulli random variable. And notice that in the natural coupling, Bk star of T1 is 0 if and only if there is no mutation on the shortest path in T that connects K and the coalescent tree restricted to K minus 1 in the natural coupling. So this is saying if we sum the Bk star from K equal to 2 up to n, and we add 1, then this is nothing but the number of blocks in the allelic partition restricted to n, almost surely. On the other hand, the Bk dagger, so in the temporal coupling, has the same distribution as the Bernoulli trials from Feller's coupling. So in both cases, we sum the Bk from 2 to n to the T2, we add 1, and we denote this quantity by K and T. So now for our main result, we have now coupled the K's and the S. So if we look at the joint vector of K and S and T, we subtract the vector S1, S2, T1, T2, the whole thing times log n, and we divide by the square root of log n. Then as S and T range over the unit square, this is going to be a random process. And in fact, as n ranges, this is going to be over the natural numbers, this is going to be a sequence of random processes. And our main result is that this sequence of random processes converges to to a two-dimensional random process, B as Bt, where again, S and T range over the unit square. And B is nothing but the one-dimensional Brownian sheet. Thank you very much for your attention.